atom, including the atomic theory and how the subatomic particles were discovered. Back in prehistoric times, they started to develop tools with various materials, such as bones and wood. They also discovered fire, which is combustion, and they used it for cooking. At approximately 10,000 BC, they learned how to brew and ferment. And then finally, 4,000 BC, they learned about metallurgy, and they were able to make bronze. However, there was no understanding of how this was happening or why it was happening. In ancient Greece, 6th to the 3rd century before Christ, the theoretical model for the modern world came about. It was not based on religion or myth, and they had 4 primary elements: fire, water, earth, and air. They used it to explain properties, such as water is cold and wet, and it evaporates to air when it was heated. However, it can't be used to predict, nor it could be tested by experiment. It was all based on speculation. At approximately 5 BC, Democritus and Leucippus came up with the original atomic theory. They referred to it as atomos, which is how we get the word atom. And it meant indivisible, by definition. It stated that matter is composed of atoms separated by empty space in which they are able to move. Atoms are solid, homogeneous, which means uniform, unchanging, and individual. All changes in matter are due to changes in how these atoms are grouped together. And different kinds of atoms differ in shape and in size. Finally, the properties of matter reflect the properties of the individual atom. Again, they can't test this. They can only speculate about it. Now we fast forward to the Industrial Revolution of 1600 to 1700. Here they have the development of precise measuring instruments, which really helped the whole notion of science altogether. They also came up with a metric system, which is what the SI system is based upon. And they had the birth of a true science. In 1661, during this period, from England, Robert Boyle started to work with the atomic theory a little bit closer. He determined that there were problems with the original Greek model of the elements. For instance, you can't extract from these substances, and you can't use it to form all other substances. From here, he developed a new definition of an element. Any substance that can't be decomposed into simpler substances by a chemical reaction was considered an element. A compound, just like the Greeks said about grouping, contained 2 or more elements. Antoine Lavoisier, shortly after this time period, in 1789, determined the law of conservation of mass. He stated that a chemical reaction, matter is neither created nor destroyed. Instead, the atoms are rearranging so that the atoms that are there at the beginning are still there at the end. They're just in different compounds. They're bonded to different things. Therefore, the mass is the same at the beginning as it is at the end. For instance, if we take silver nitrate and we combine it with sodium chloride, the sodium is still there on the right when it made sodium chloride, and the nitrate's still there on the right when it made sodium nitrate. All the atoms are still accounted for. They still have the exact same amount of atoms. So if you look at the scale up here, before they got mixed together, it was 300.23. After they were mixed together, it was still 300.23. So the actual masses did not change, even though they don't look the same anymore. Then Joseph Proust, from 1754 to 1826, came up with the law of definite proportions. This states that all samples of a given compound, regardless of their source or how they were produced, have the same proportions of their constituent elements. So we're looking at mass ratios when we're looking at the definite proportions. And this led to the difference between a compound and a mixture. A mixture does not have constant composition. It's an intensive property. Remember before we talked about intensive properties being that they do not depend on the size. So something like density or color would be an intensive property. And what Proust was saying is that mixture have intensive properties where they vary depending on the composition. So the difference in the coloring could have a difference in the mixture itself. It contains two or more elements and or compounds that can be separated or purified by physical processes, like evaporation used in heating or hand sorting, but not by chemical means. Compounds, however, are pure substances, which include compounds and elements. They are a fixed set of intensive properties, unlike the mixture, which can vary. And they obey the law of constant composition. What that means is that if we have C2H6, this particular compound, which is ethane, will always have 2 carbons and 6 hydrogens. Once that composition changes, it's no longer that compound. It's a new compound. So if we have 100 grams of water, and 11% of that is hydrogen, then what's the mass of hydrogen? You just simply take 100 times 0.11, and we got that from 11% divided by 100. Took it out of a percentage, and that comes out to be 11 grams of hydrogen. We could do the same thing with hydrogen chloride. If we have 100 grams of hydrogen chloride and 3% of it's hydrogen, so 100 times 0.03 is equal to 3 grams being hydrogen. What's the mass of chlorine? Well, if 3 grams of this is hydrogen, then the remaining 97 must be chlorine. Then John Dalton came around in 1804, and he determined the law of multiple proportions, which states when 2 elements, let's call them A and B, form 2 different compounds, the mass of B that combine with 1 gram of A, so we're always dealing with 1 gram, can be expressed as a ratio of small whole numbers. So we have 2 different compounds, and we're comparing the 2. So different compounds, even though the elements are the same, have different ratios. For instance, nitrogen forms several compounds with oxygen, including nitrogen dioxide and dinitrogen monoxide. Nitrogen dioxide contains 2.28 grams of oxygen for every 1 gram of nitrogen. Notice they made it 1 gram. While dinitrogen monoxide contains 0.57 grams of oxygen for every 1 gram of nitrogen. Show that these results are consistent with the law of multiple proportions. So, we're comparing the amount of oxygen in one compound to the other. So 2.28 grams over, and that's in the nitrogen dioxide, 0.570 grams, and that's in dinitrogen monoxide. We divide that out, and that comes out to be 4.00. So because it does create a small whole number ratio, it does actually follow the law of multiple proportions. And in this process, he developed the new atomic theory. Dalton proposed a theory of matter based on having ultimate indivisible particles to explain these laws. There are 4 parts to this theory. Each element is composed of tiny, indestructible particles called atoms. Now notice that this is back in 1804. We have learned a lot of stuff since then. So there actually are ways that we can destroy atoms. For instance, we have nuclear power, and we'll discuss that kind of stuff later in the semester. All atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. Which again, even though he was really close, there were some issues with this because now we know that we have isotopes. So he wasn't 100% right again. Atoms combine simple whole number ratios to form molecules of compounds. That's pretty much true. They do come together to create compounds. In a chemical reaction, atoms of one element cannot change into atoms of another element. However, we do know this a little bit if it's a nuclear reaction. But what he was really getting at is the fact that the atoms will rearrange and combine with other atoms to create new compounds. That brings us to the modern definition of an atom. It's the smallest piece of an element that retains the properties of the element. It's the building blocks. And there are things inside of the atom we know now. We have electrons, protons, neutrons, and a nucleus. And now we're going to start discussing how these were discovered. J.J. Thomas, from 1856 to 1940, used a cathode ray tube to discover the electron. It's almost like a neon light. It's a glass tube containing a metal electrode from which almost all the air has been evacuated, so it's vacuum here. When it's connected to a really high voltage, a glowing area is seen in the tube itself. So like I said, it's like a neon light. J.J. Thomas believed that the cathode ray was composed of tiny particles with an electrical charge. He designed an experiment to demonstrate that there were particles by measuring the amount of force it takes to deflect their path a given amount, like measuring the amount of force it takes to make a car turn. Notice down here, he has a magnet next to the cathode ray tube, and instead of the line going straight across, it's being attracted to that magnet. He investigated the effect on the cathode ray of placing an electric field around the tube. This is the magnet that we were just looking at. The charged matter is attracted to this electric field. Light's path is not deflected by an electric field. Light's path is typically not deflected by an electric field. So he determined that there was a negatively charged particle with a very low mass, and they called this the electron. Robert Millikan in 1909 came around and determined the exact charge of the single electron and the exact mass of a single electron. And so that brought us to the Plum pudding model that Thomson discovered. He has little negative areas in here, and he put this all in an electron or in a positively charged cloud. So all the positives are all over it, and there's little negative dots around it. In the late 1800s, Henri Becquerel and Marie Curie discovered certain elements would constantly emit small energetic particles and rays, and this could penetrate matter. And then in 1909, Ernest Rutherford. So notice that the time frames here keep speeding up more and more and more because more is discovered, and we have better equipment as time goes on, so we can still discover more things. Anyways, Ernest Rutherford did the gold foil experiment. Here we have the alpha particles. It's basically a helium atom with no electrons. So it's just the nucleus itself. He thought once he removed the electrons, if he shot it through a piece of gold foil, which is a lot like aluminum foil, it's just made out of gold and it's pounded really, really, really thin, he thought the particles would go straight through without any deflection whatsoever. But what he noticed is that things were reflected off, and some of them shot all the way back. So that means that there was something inside the foil that was interacting with something inside the alpha particle. And so he realized then that the electrons were actually most of the space, and there was actually empty space in there. And that's how he came up with the nuclear atom. It's an atom that is mostly space because almost all the particles went straight through. An atom contains a very dense particle that was small in volume compared to the atom but large in mass. And this was because of the few particles that bounced back. The dense particle was positively charged because of large deflections of some of the particles. The atom contains a tiny dense center called the nucleus. The amount of space taken up by the nucleus is only about one-tenth of a trillionth in volume of the atom. The nucleus has essentially the entire mass of the atom. The electrons weigh so little they give practically no mass to the atom. The nucleus is positively charged. The amount of the positive charge balances out the negative charge of the electron. So this is what Thomson was saying here. He was saying that the positive and negatives were canceling out. He, however, with the plum pudding, thought it was a cloud of positive, whereas Rutherford came in and said that all the positive was in the middle. The electrons are dispersed in empty space of the atom surrounding the nucleus. Rutherford proposed that the nucleus had a particle that had the same amount of charge as an electron, but opposite side. Based on these measurements of the nuclear charge of the elements, these particles are now called protons. And they are almost the same charge as the electron, but they're much greater in mass. Since protons and electrons have the same amount of charge, for the atom to be neutral, there must be equal numbers of protons and electrons. So we can compare sizes to each other. The scale of comparison is called the relative scale. So we can compare the charge of a particle to electrons, which is considered a -1 charge unit. The proton has a +1 charge unit. Proton's charge is opposite in the same magnitude as the electron. So basically what this is saying is, instead of dealing with all those itty-bitty numbers in the previous screen, times 10 to the 19th, times 10 to the -24, we're going to say that we're going to compare them by whole numbers because it's easier. We generally talk about the mass of atoms by comparing it to 1/12 of the mass of a carbon atom, with 6 protons and 6 neutrons, which we will call the 1 atomic mass unit, or 1 AMU. Protons have a mass of 1 AMU. But if we compare that to an electron, electrons have a mass of 0.00055 AMU, which is really small in comparison, and generally too small to be relevant. Neutrons, we noticed that the masses did not add up properly, therefore there must be something else in there. To answer these questions, Rutherford and Chadwick proposed that there was another particle in the nucleus called the neutron. Neutrons have no charge whatsoever, but they have a mass of 1 AMU. So they have the same, very similar mass to that of the proton. It's slightly heavier than the proton, but very similar, and no charge. So here is a general summary of the subatomic particles. We have protons, electrons, and neutrons. Notice we have, for protons, 1.67262, 1.67493 times 10 to the -24. So they're very, very similar, whereas the electron is smaller. So if we then convert this over to AMUs, the neutron and the proton are very similar once again, whereas the electron is very small. The proton and the neutron together create the nucleus. And then the electron is in the empty space around the nucleus. charges, we have +1 for proton, -1 for electron, and then the neutron doesn't have a charge. Now these you will see time and again throughout the semester, so you might want to get familiar with the abbreviations for these. And that gives you an overview of how the particles were discovered and what makes up the atom.